Hey, welcome to high school physics. My name is Rex. In case you're meeting me for the first time, I wrote my high school external examination when I was 13 and I cleared my papers. I'm 14 now and I'm too young to go to university, so I just keep reviewing my subjects like physics, chemistry, biology, and so on. I'm here for us to learn together as I teach you what I've learned across high school, and we learn together as we explore high school physics, high school chemistry, high school biology, and so much more. So let's dive into it. So today we're going to be studying fundamental and derived quantities, types of fundamental and derived quantities, and units and measurements of fundamental quantities. Before I dive into units and measurement, I'd like to explain what physics is. Physics is the study of everything around us. And if you want to study everything around you, you have to measure those things. Either its length, its width, its volume, or the time it takes an object to get from point A to point B. This is what units and measurement help us to do in physics. So, measurement is very essential in our everyday life. And without measurements, then it's practically impossible to study physics. Now, physics and measurement work hand in hand. When we measure things, measurement comes in quantities and units. It means that if you say that the length of a rod is 10 centimeters, it means that it has a quantity and it has a unit. The quantity in this case is 10, and then the unit is centimeters. Physics usually use standard units called SI units. This is the standard unit agreed by physicists all over the world that they use to measure objects around us. There are two types of quantities and units. There are the fundamental quantities and then the derived quantities. Let's dive into the fundamental quantities. What are fundamental quantities? Fundamental quantities are those quantities that are independent by themselves and only need instruments for measuring them. There are 6 fundamental quantities, namely length, mass, and time. These 3 are the basic fundamental quantities in physics. Then we have temperature, electric current, and then amount of a substance. These fundamental quantities have their units. The unit of length is meters, m. The unit of mass is kilograms, kg. Unit of time is seconds. Unit of temperature is Kelvin. Then electric current is amperes. And amount of a substance is moles or mol mol period. We're going to get into moles deeper when we study chemistry. Now, length, mass, and time, like I said, are the basic fundamental quantities because they are the quantities that help shape the derived quantities. Now let's dive into the derived quantities. Derived quantities are those that are dependent on the fundamental quantities. It means they don't have meaning on their own unless they get it from the fundamental quantities. Now, there are 3 examples of how to get derived quantities. There are the fundamental multiplied by the fundamental, there's the fundamental and the derived, and then there's derived and derived quantities. An example of 2 fundamental quantities to form a derived quantity is area. Area is length times length, or length times breadth if you studied mathematics. But in physics, we treat length and breadth as the same thing, so they're both length. And we studied just a few minutes ago that length is in meters. So this is meters multiplied by meters, to give us meters squared. Another example is fundamental quantities coming together with a derived quantity to form a derived quantity, and that is force. Force is mass times acceleration. Like we studied before, mass is in kilograms, and acceleration is a meter per second squared. I know we haven't studied this, but it's just from my basic knowledge of physics. I'll get deeper into that as I explain. And if you multiply these 2 quantities, you get kilogram meter per second squared, or newtons. We generally measure force in newtons, so it's safe to say that force can be measured in newtons. And lastly, 2 derived quantities coming together to form a derived quantity is pressure. Pressure is force divided by area, which is Newton divided by meters. Remember that force was newtons and area is meters squared. So this is Newton divided by meter squared to give us Newton meter raised to the power of -2. Other examples of derived quantities are density, momentum, and energy. There are millions and millions more of derived quantities. Why? Because as long as we follow these steps of fundamental and a fundamental and a derived, and 2 derived, we're always going to arrive at the derived quantity. If you break these 2 derived quantities down, you're still going to end up with a fundamental quantity. Let me explain. When we talked about force, we said force was mass, which is the fundamental quantity, and acceleration, which is the derived quantity. If we break acceleration down, we're going to get that acceleration is velocity divided by time. That is how to find acceleration. Now, velocity is a derived quantity. Time is a fundamental quantity. We have to break velocity down into its fundamental quantities. Velocity is distance divided by time. Now we have just broken it into its two fundamental quantities: distance, which is in length or meters, and time, which is in seconds. So each time you break a derived quantity, you're always going to end up with a fundamental quantity. So you're always going to get much more derived quantities from different derived quantities. Now we're going to talk about length. In this topic, we're going to focus on length, mass, and time as the three basic fundamental quantities in physics, and we're going to focus on its instruments. So length is the measurement of the distance from point A to point B. There are different instruments used for measuring length. And before I dive into the instruments used for measuring length, I'd like to explain what a reading accuracy is. The reading accuracy of an instrument is the smallest graduation that instrument has and can still remain correct. It means that as you see these tiny lines over here, these are the smallest graduations that the instrument has. Even in the vernier calipers and in the micrometer screw gauges, you can see all these little lines. These are the graduations, and these are also the reading accuracies. So there are different instruments. There's number one, the meter rule and the calipers. There's the vernier caliper, and then there's the micrometer screw gauge. The meter rule, we practically use the ruler. It's like a short form of a ruler, and we practically use that every day. The vernier caliper is a much more complicated instrument, and it has a smaller reading accuracy. For the meter rule, the reading accuracy is either 1 millimeter or 0.1 centimeters. They're practically the same thing, just with different units. This one is in centimeters, and this one is in millimeters. Vernier calipers have a reading accuracy of 0.01 centimeters or 0.1 millimeters. It's a tenth lower than the meter rule. Now the caliper doesn't really have a graduation because it's not an instrument for measuring length. It's used for measuring diameters of circles. So a caliper has a jaw. It's like a C, and it's kind of like this micrometer screw gauge, only it doesn't have all these iron parts. It can easily open and close, and these are used to measure the inner diameters or outer diameters of circles. Now when you get the diameter of the circle by closing the jaws, you can just place them on the meter rule and measure its length. The micrometer screw gauge has a reading accuracy of 0.01 millimeters or 0.001 centimeters. A fun fact, the micrometer screw gauge can actually measure the thickness of a piece of paper or even the thickness of your hair. Now that's really small. The volume of an object is the space an object has, and this is another aspect of length I haven't talked about. Let's talk about volume as an aspect of length. Volume can be measured on regular solids or irregular solids. The volume of regular solids, such as cubes, cuboids, spheres, pyramids, cones, and so much more, they have their standard formulas for measuring the volume. So for cubes can be measured by length multiplied by the breadth multiplied by the height. That's LBH. Length multiplied by breadth multiplied by height. The standard formula for measuring the volume of a sphere is 4/3 pi r cubed, or 4/3 multiplied by pi r cubed. And there are other solids, but I won't get deep into them so we can save time. For an irregular solid, such as a stone or any other irregular solid, we use what is called liquid displacement. What is that? Well, it's practically getting a beaker. It's actually explained here. It involves filling a beaker with water and recording its volume, placing the solid in the beaker and recording the volume of the liquid displaced. So to simplify what I just read, it's practically getting a beaker, filling it with water, and recording its volume. Once you've recorded the volume, you place the solid you want to measure its volume inside the water, and of course the water would rise to a certain extent. Then you measure the rise of the water. That is, you measure the volume of the water displaced. You measure the new volume. So let's say you brought a beaker and filled up water to like 20 centimeter cubed, and then you added the irregular solid and it rose to 40 centimeter cubed. So you recorded the 20 centimeter cubed and the 40 centimeter cubed. The difference between the old and the new recorded volumes is the volume of the solid. So the difference between 40 and 20 is the volume of the solid you're looking for. The difference between 40 and 20 is 20. So the volume of the solid you placed into the water is 20 centimeter cubed. Volumes of liquids can be measured with instruments like pipettes and burettes and measuring cylinders. These are instruments used in the laboratory for titration of acids and bases, and I don't have the picture of them right now, but we'll get deeper into them as I get into chemistry, because they have a lot of that in chemistry, especially when it comes to titrations. Mass and its instruments. So now that we're done with length, Mass and weight are often confused with each other, but know that these are entirely different terms. Mass is the study, sorry, mass is the amount of matter in a body, is the amount of stuff something has. But weight is the force of attraction a larger object has on a smaller object. Alright? So I can say that my weight is the attraction the earth has on me, right? But my mass is not my weight, alright? Force is also known as weight. Like force and weight are the same thing. That's why weight and mass are not. Now that we've clarified that, there are different instruments used for measuring mass, like beam balances, scale balances, like you saw in the very first slide, and spring balances. They're usually used in airports to measure the weight of traveling bags and suitcases, and these have a reading accuracy of 0.1 gram or 1 milligram. Time is used to record different events at different points of time. Okay, there are different instruments used for measuring time. There's a stopwatch, there's a stop clock, and then there's watches, and there's also clocks. Basically anything that you can use to tell time, right? And these have a reading accuracies of 0.1 seconds. And finally, I'd like to talk about dimensional analysis. Anything that has a unit of length also has its dimension of length. So the dimensional analysis of an object is the dimension of length, mass, time, or any other fundamental quantity it has, or even derived quantities. So the dimensional analysis for length is L, the dimensional analysis for mass is M, and the dimensional analysis for time is T. Now that we've gotten these three basic fundamental quantities and their dimensions, we're going to use them to get out the derived quantities we brought in earlier, which are area, force, and pressure. So area is length times length, and the dimension for length is L. So the dimension for area is L times L, which is L squared. Force is mass times acceleration. The dimension for mass is m. The dimension for acceleration is, okay, I said that the unit for acceleration is meter per second squared. Meters is measured in length, and seconds is measured in time. And because it had the -2 at the top, it's going to be LT raised to the power of -2. So the dimension for acceleration is LT -2. So if you multiply these two things, we're going to get MLT raised to the power of -2. And now with MLT raised to the power of -2 and L squared, we're going to divide them to get pressure, because pressure is force divided by area. When we divide these, the L at the bottom is a squared, while the L at the top is just 1. So we're going to cancel out one L here and cancel out L. So L is going to be removed from the top, and we're going to be left with MT raised to the power of -2. But we have one L at the bottom, so we're going to divide it by L to get ML raised to the power of -1, T raised to the power of -2. This is the dimensional analysis for pressure. And finally, we've arrived at the questions. Number 1, list 3 fundamental units. Okay, I'm not going to say that. You're going to write that in the comment section. And then 2, list 3 derived units aside from pressure, area, and force. I intentionally wrote this aside for pressure, area, and force because I don't want you going to look at the slides again and try to copy the units. There are billions of derived quantities, so you can do some research and even write more, all in the comments section. And last one is to distinguish between mass and weight. We distinguished them when we were talking about mass and its instrument for measuring mass, and now you're going to write that in the comment section as well. If you enjoyed this class, please subscribe, like, and share with at least 3 people you know don't have basic education or who is able or bold enough to explore homeschool. See you in the next class.